Hello friends, once again I welcome you to our ongoing journey on Six Sigma, and I would like to remind you that we are in the final phase of our DMAIC cycle and we are discussing the various issues in the control phase. Mainly we are focusing on statistical quality control. As a part of that, we have talked about statistical process control, control charts for variables and control charts for attributes. Now we are talking about acceptance sampling. We have seen the key concepts like producer's risk, consumer's risk, AQL, OQL and couple of other things in the last lecture. Now this particular lecture 55 will focus on design of acceptance sampling plan for attributes. As we need to discuss in detail and there are lot many things to cover, this particular lecture is divided into part 1 and part 2. So let us begin with lecture 55. Once again I would emphasize that there is no substitute of control chart, and statistical process control and acceptance sampling are must in order to have fact based management in the organization. So this is what we have covered, and we also had little bit glimpses on types of sampling plan and that key characteristic, and we had seen some of the evaluating criteria for sampling plan. So this lecture will basically focus on lot by lot attribute sampling plan, and we will talk about single sampling plan, double sampling plan and multiple sampling plan. Our focus mainly is on the design of the sampling plan, typically under the category of lot by lot attribute sampling plans. So choosing a sampling method is an economic decision. I cannot go with 100% inspection, but obviously say I have to see the trade off between producer's risk and consumer's risk, and single sampling plan there is a high sampling cost. Double multiple sampling plan, I may take a decision on a very first sample and my sample size would be less, so my sampling cost is little bit lower compared to the single sampling plan. Now if you see the lot by lot attribute sampling plan, then these plans are designed to make a decision regarding items that are submitted for the inspections in lot. So typically if you see the batch production, then items are produced in lot and then they are submitted for the sampling and inspection decision making in a particular lot, and the objective is to find here sample size and acceptance number of a sampling plan which is acceptable to both producer and consumer. Once again I would like to remind you that producer's risk is type 1 error denoted as alpha, and producer would not like his good quality lot to be rejected. Consumer risk is beta type 2 error, and consumer would not like the bad quality lot to be accepted. So we have to see the trade off between producer's risk and consumer's risk, and unless you consider the judicious trade off between these two, you cannot really design a sampling plan with sample size and acceptance number and rejection number and other criteria. So the whole exercise we will do in this particular lecture is all about to see that how producer stipulated risk and consumer stipulated risk can be appropriately accommodated so that I can devise a judicious, logical and mutually acceptable sampling plan to both the parties. So this is exactly we will try to do. So we have broadly say 4 different categories of lot by lot attribute sampling plan: single sampling plan, double sampling plan, multiple sampling plan and standard sampling plans. So there are totally 4. In this particular lecture we will focus on these 3, that is single sampling plan, double sampling plan, single, double and multiple, and we will focus on standard sampling plan in the next lecture. So this is what we want to do. Now let us see the design of the single sampling plan, which is easiest to employ, but because we only rely on single sample and sample size may be larger, so the overall cost of inspection may be more compared to the double sampling and the multiple sampling, but so far the administration is concerned, single sampling plan is the best to use and implement. So the overall picture goes like this. In single sampling, I have the lot of n items and then I have random sample of n items, that is the small n. Now I inspect it. After inspection, I will find that there are C dash defectives found in the sample. I can also replace the defectives as a part of my rectification process, but here just try to focus on this, that C dash is the defectives found in the sample. Now if this C dash is less than or equal to C, which is the acceptance number, I will accept the lot, because it is less than the acceptance number and I will accept the lot. If it is greater than C, means number of defectives, then I will reject the lot. And you can have n non-defectives from a lot of say capital N and a sample of n. So this is what exactly I do in a single sampling plan, and it is called single sampling because I just collect one sample, and then based on that I try to compare the number of defectives in the sample with the acceptance number and make my decision. So single sampling plan basically deals with a decision regarding a lot of size n and sample size n, and you have the acceptance number C to decide that whether this is accepted or this is rejected. So typically if you see the operating characteristic curve, which is a measure of performance either of control chart or the acceptance sampling plan, basically it provides the discriminatory power. I am repeating this statement again and again to my acceptance sampling plan, and how discriminatory it is in terms of say separating the good lot from the bad lot, and this is what we try to appreciate as a part of operating characteristic curve. So if we just see the couple of issues that we discussed in the last lecture, then one of them was AOQ or AQL, that is acceptable quality level. So acceptable quality level is the measure of a good lot, and typically it is associated with the producer's risk alpha. So my producer would not like a good lot to be rejected, and AQL acceptable quality level is typically the one which is associated with producer's risk, that is alpha. If you look at the another definition, that is LQL, this is limiting quality level, then this is the measure of a poor lot, and typically it is associated with the consumer's risk, and consumer would not like a poor quality lot to be accepted. So in the previous lecture we had average outgoing quality level. These concepts we have seen. Now I am introducing two more new terms. One is acceptable quality, other is say your limiting quality level, that is LQL. Now suppose I consider a sampling plan specified by N and C lots with a proportion non-conforming level of AQL that come in for inspection should be accepted 101 minus alpha % of the time. It means number of lots coming for the inspection, and out of these many lots I will select 101 minus alpha % of the time out of these submitted lots, and this is something which refers to my AQL. So same way I can say that AQL is 0.03 and alpha of 0.05. So I would say that lots that are 3% non-conforming should then be accepted 95% of the time by the given sampling plan. So you may make a mistake, 3% is the level that you need to achieve, that is the acceptable quality level, and let us say if it is 0.03, 3% and I operate with a particular level alpha, it means the lot is of good quality, type 1 error, but I will reject it. So, I will say that if my alpha is 0.05, that is 5%, then the lot which contains 3% non-conforming or defective, 95% of the time it should be accepted, and that is what my operating characteristic curve or my acceptance sampling plan must incorporate. So, this is the clear cut understanding. Similarly, if the proportion of non-conforming of the batches coming in for inspection is LQL, now let us think from the consumer's point of view. Suppose I am referring the limiting quality level, this is the quality of a poor lot. So, let us say LQL, they should be accepted by 100 beta %, means the bad quality lot should be accepted by 100 beta %. Let us try to appreciate. LQL is 0.09 and beta is 0.1. So, what would I say? That the lots that are 9% non-conforming, 9% non-conforming should be accepted only 10% of the time. So, the idea is very clear. Let us say AQL 0.03, that is 3%, and if I have the alpha is equal to 0.05, I will say the number of lots submitted, out of this number of lots, the lots having 3% defective or non-conforming, 95% of the time it should be accepted. It is only 5% time producer's risk will come in picture and I will take the wrong decision. Similar way, if I refer the bad quality lot, let us say 9% is LQL and beta is my 10%, 0.10, then I will say that the lots which has 9% defective, this lot should only be accepted 10% of the time, so that my consumer's risk remains at 10% and he feels protected. So, it is all about protecting your producers and consumers, and I would say that what is the level of protection your acceptance sampling plan ensures to your consumer and producer and acceptable to them decides the goodness of your acceptance sampling plan. So, this is something which is very important and you must appreciate. Just see the OC curve for AQL 1 minus alpha, that is specific to your producer's risk, and LQL beta, that is specific to your consumer's risk. You can see it very well here. AQL is this and this is my alpha, that is producer's risk. It means that the lot which has this much %, you see proportion of non-conforming, the lot which has this much % of non-conforming AQL, it will be accepted 95, 96, whatever is this alpha as per that many times. But the lots which has LQL quality level, that is very poor lot, maybe let us say 9%, 8%, whatever, then it would only be say accepted this much of the time, and this is my basically probability of acceptance. So, I hope the idea is crystal clear that a producer would like the lot to be accepted at AQL and he would not like any lot to be rejected if it is below AQL or at AQL, and similarly a consumer would not like to accept the lot which is of very poor quality LQL with beta % risk. So, again I would remind you that we are dealing with the probability, we are dealing with the sampling, and we always take the decision or test the hypothesis by accepting some level of type 1 and type 2 error. We cannot get rid of say making the error, but we can just try to see that how these errors can be kept at minimum level, and this is acceptable typically in acceptance sampling plan to my both producer and consumer. So, this is something that I wanted to emphasize. Now, if you see the design of a single sampling plan, then there are three issues. Number one, stipulated producer's risk. So, let us say AQL is something related to producer's risk alpha, we have seen in the figure, and consumer's risk, that is beta, specific to your consumer, and you may have stipulated producers and consumers risk. So, now when I want to design the single sampling plan, meaning to say I want to decide about sample size n and the acceptance number c, I have to consider three different situations, or one of these three. Either I design it for stipulated producer's risk, it means my plan will exactly try to meet the producer's risk, or I may try for consumer's risk, or I may try to incorporate both simultaneously. So, let us try to see how we can design the single sampling plan with these three different criteria. So, let us see the first one, design of single sampling plan based on stipulated producer's risk. So, stipulated producer risk, you know, it is say given by alpha, associated quality level P1, which is basically AQL, and I would like the lot containing P1 non-conforming to be accepted 101 minus alpha percentage of time. In a very simple way, if your type 1 error alpha producer's risk is 5%, then I would like the lot having AQL percent defective to be accepted 95% of the time. Now, what would I expect here, that we want to find a sampling plan whose OC curve will basically pass through the point which is tagged as AQL 1 minus alpha. Now, remember that this criteria is not very restrictive. The OC curves of a variety of plans could pass through this point. So, you may have different sample size, you may have different acceptance number. So, you cannot say that would be only one OC curve that will pass through this particular point AQL 1 minus alpha, but there could be multiple plans that you can devise. But my point here is to see that how best I can address the producer's stipulated risk in designing my single sampling plan. So, with this let us try to move ahead, and what I would like to do to find the appropriate sampling plan, first select an acceptance number, that is the C. The procedure I am just going through. The Poisson distribution will be used to approximate the hypergeometric distribution when determining the lot acceptance probability. So, we have done this exercise previously also. So, your Poisson distribution table will have mean as well as the value, individual value. By looking at this, you can figure out what is the probability of acceptance, and this will give you the cumulative probability from the Poisson distribution table. Now, mean number you can find for referring the Poisson distribution table, that is lambda is equal to NP and PA equals to 1 minus alpha. So, you have a probability of acceptance and P is equal to P1, that is the value of lambda found in the Poisson distribution table. Now, here because you have P, that is AQL, so I will say lambda is equal to NP is equal to N into AQL, and this is what you will try to refer when you will see the cumulative Poisson distribution table. So, now let us try to see this through example. So, when you see the numbers, the idea is better clear. Now, find or design a single sampling plan that satisfies the producer's risk 5% as usual, and you have the lots with 1.5% non-conforming. So, you are given these two value alpha 5% and the lots with 1.5% non-conforming. We are supposed to design single sampling plan. So, here I would refer a particular standard table. We are not interested in seeing how this table has come, but I will refer a particular standard table of values of NP for a producer's risk of 0.05 and consumer risk 0.1. This particular table is developed and published by F.E. Grubbs in 1949, long back, on designing single sampling plans, and it was published in Annals of Mathematical Statistics. So typically I will have two things here. One is the NP1, values that are used for deriving single sampling plan that satisfies the producer's risk, and NP2, these are used for deriving single sampling plan that satisfies the consumer's risk. So this researcher F.E. Grubb has designed a table, standard table, which can help us to find the value of NP1 and NP2 for the producer's risk and respective say consumer's risk respectively, so that we can easily figure out our single sampling plan for a stipulated producer risk or a stipulated consumer risk, and also we can use this table to find a plan which meets the stipulated producer and consumer risk both. So we have three conditions for which we will try to develop the single sampling plan. So now just see the table, and what it tells, you have the acceptance number in the first column and you have NP1 for PA is equal to 0.95. So 1 minus alpha percentage, it means I am referring to the producer's risk, and these are the values specific to NP1. It is a standard table, so we just accept it in order to design our single sampling plan. NP2, it is for 10% beta, you can see here 10% beta, and this is for used for my stipulated consumer risk based single sampling plan. You will see the third column where you have NP2 divided by NP1. This we will use for devising or developing the single sampling plan which can accommodate stipulated producers as well as consumers risk. So now the thing is very simple, that we have this table, and now the data given is like this: alpha is equal to 0.05 and you have P1 is equal to AQL 0.015. So 1.5% defective is 0.015. So this is my P1 is equal to AQL, and I have alpha is equal to 0.05. Now just refer the table, and for C is equal to 1, what do you find? So let me go back to help you. So for C is equal to 1, what you find here is 0.355. We will only refer this particular column which I have highlighted in pink. When we will talk about the next case, I will highlight this second column. Third case, I will highlight third column in pink, so that you can focus on that particular column. So here you can see that the value of NP1 is basically 0.355. So once you get this value from the table, you just see here that for C is equal to 1, NP1 is 0.355. So I can just rewrite it like this, and my P1 is 0.015. So I will have 24 as the sample size. Now let us say if our acceptance plan is C is equal to 3, acceptance number is C is equal to 3, then I will get corresponding NP1 1.366. Let us verify so that you become crystal clear. So for C is equal to 3, you can see that C is equal to 3, it is 1.366. So I hope now the idea is clear, that I am taking the value for different C, the value of NP1, and this is 92. Same way this will be 220 for C is equal to 6. Now once I have done this calculation, you can easily plot your operating characteristic curve for single sampling plan for stipulated producers risk and AQL. So I referred AQL, I referred Grubbs table for typically stipulated producers risk, and this is where I get the probability of acceptance, probability of non-conforming, I get n is equal to 24 for C is equal to 1, this is the OC curve. Then n is equal to 92, C is equal to 3, this is the OC curve. N is equal to 220, C is equal to 3, this is the OC curve. You can see that as the sample size and increases, I am going for steeper and steeper operating characteristic curve. It means my discriminatory power increases, and this is exactly I told that not necessary that you will have only one OC curve passing through a point AQL and 1 minus alpha %, but you can have multiple OC curve depending upon sample size n and the acceptance number C. So now out of this, which one to choose depends on the criticality of the quality characteristic and the consequences that it may have on the final quality of the product. So depending upon that, you can decide or you can choose judiciously the discriminatory power of the single sampling plan. So when you have understood this, let us try to apply the same for the second case, and second case is stipulated consumer's risk. Now here same way I will try to follow the procedure, but I will refer the beta and P2 is equal to LQL. So my limiting quality level typically indicates that the bad quality lot at some beta % consumer's risk, and this is what I will try to use. So my beta is 0.1 and I will try to find NP2 from the Grubbs table so that I can figure out my particular acceptance sampling plan. So let us see the example, and it would be clear that single sampling plan that will satisfy a consumer's risk of 10% for lots that are 8% non-conforming. So I will once again refer this particular table, and if you see I have now highlighted the second column in pink. So I have to refer this because NP2 is specific to consumer's risk and I have been given the value of consumer's risk 0.1. So what I get here, when I refer the table for C is equal to 1, I get the value NP2 3.890, I get n by putting value in this. Similar way for C is equal to 3, I get n is equal to 84, 6 I get this. So finally you can figure out an acceptance sampling plan for single sampling with n is equal to 132, n is equal to 84, n is equal to 49, and what do you see here? My sample size is reducing, but this is 132, this is 84, this is 49, but simultaneously my value of C is also reducing, and you will find that the combination of these two is giving me a better discriminatory power. So here it is not straightforward what we have seen, that you increase the sample size for producer's risk and your curve becomes steeper. Here even though the sample size is decreasing, or if you say increasing, my curve is not behaving like that, but simultaneously you should see the effect of C, and you will find that for this beta my consumer's risk, and this is the limiting quality level, I have 3 different OC curves which is passing through this LQL point. So LQL and beta basically say designs my single sampling plan for stipulated producers consumer's risk. Now let us see the third case. I want to design a plan for stipulated producers and consumers risk both. So now what I want a plan basically which satisfy a producer risk alpha given an appropriate quality, that is P1 is equal to AQL, and also consumers risk beta given an associated P2, that is LQL. So now I want to consider both. Previously I considered only AQL, that is P1 and alpha. In the second one I considered LQL and then beta. Here I want to consider both my LQL as well as AQL, beta and alpha. So for this I would first try to present the operating characteristic curve, and what it indicates that my sampling plan, whatever I have, let us say n is equal to 45 and c is equal to 2, n is equal to 75 and c is equal to 3, and n is equal to 76, c is equal to 3, n is equal to 60 and c is equal to 2. So now here you will see that there are two plans which are indicated in dotted, and there are two plans which are indicated in full black line. So if you see the plans which are indicated in dotted, they are passing through this particular, that is the AQL, and the plans which are in dark line, they are passing through this. Now I have to select both in such a way that a proper trade-off can be set when I select a particular plan. So this is really interesting, and you have two plans which satisfies the stipulated risk indicated in dotted, stipulated risk of producer, the plan indicated in full black, stipulated risk of my consumer. So now let us see how we can go ahead. So I want to figure out basically the plans which can best satisfy the stipulated risk of producer and stipulated risk of consumer. So two plans meet the producer stipulated risk as I mentioned in dotted line, and two plans in full line, they meet the consumer stipulated risk exactly and come close to meeting the producer's stipulation. So now what happens that if I look at the dotted line, for example here, then you have two dotted curves. Let us say this is the one and this is the second one which is little bit hidden. These are the plans which exactly meets the producer stipulated risk because they are passing through this AQL, and I have the full line plan which are passing through this LQL, so exactly they meet. Now obviously I have to meet the expectation of both producers and consumer. So what I would like to do, I can design a plan which exactly meets the producer's risk and would be very close to my consumer stipulation. Similar way I can do otherwise. I would like to choose a plan which exactly meets the stipulation of the consumer and would be very close to my producer. So this is the choice what I have. Now if I just try to see it through example, then let us try to see. Find a single sampling plan that satisfies the producer's risk of 5% for lots that are 1.8% non-conforming and consumer risk of 10% for lots that are 9% non-conforming. So 5% is the producer's risk, that is the alpha, 1.8% non-conforming, that is your related to producer, consumer risk 10% and lots that are 9% non-conforming. So I will again use this particular table, and you can see that now I have highlighted this particular last column in pink. So I would be simultaneously using NP2 and NP1 in order to find a plan which satisfy my producer and consumer both. So just see what is the data given. You have alpha is equal to 0.05, P1 is AQL 0.018, beta is 0.10, P2 LQL is 0.09, and we can find the ratio NP2 by NP1. So P2 by P1 is basically LQL by AQL, and this is 5. Now let us see that where this ratio falls. So this particular ratio 5 falls between 6.51 and 4.89, corresponding to acceptance number 2 and 3. So you want to see, then let me go back. This is the say table, and just see the ratio 5. So this ratio will fall somewhere here, 5 will fall somewhere here. So this is specific to acceptance number 2 and acceptance number 3. So now what I have two acceptance number, C is equal to 2 and C is equal to 3. So I can now find C is equal to 2 and P1 value from the same table, and I can find the value of n. Similar way, C is equal to 3 and P1, and I can find the value of n. So what I get here is n is equal to 45 and C is equal to 2, n is equal to 76 and C is equal to 3. both satisfy the producer's stipulation exactly. So this is something, because I have used this NP1 which is specific to producer, so these plans exactly satisfy the producer stipulation. Now let me go ahead to this is really interesting, just do it comfortably and it would be crystal clear. Now if I refer the column 2 in order to consider the consumer stipulation, I will get C is equal to 2 for NP2 5.322 and I will get N is equal to 60. For C is equal to 3, I will have NP2 6.681 and N is equal to 75. So I can chalk out two plans from consumer stipulation point of view. One is N is equal to 60, C is equal to 2, N is equal to 75, C is equal to 3. So now it's really interesting that I am left with now 4 plans. Plan 1 and 2 producer stipulation exactly, plan 3 and 4 consumer stipulation exactly. So plan 1 N is equal to 45, C is equal to 2, plan 2 76 and 3, plan 3 and plan 4. Now what I want to figure out, I want to go by either of the criteria, and the criteria is like this. I want a plan which exactly meets the producer's stipulation and would be very close to my consumer, or a plan which would be exactly meeting the stipulation of consumer and would be very close to producer. You cannot satisfy both exactly. So it's something like if you have a 2 child and they have different requirement, you will see that okay, the requirement of child 1 is extremely critical, let me try to meet it exactly, and if the child 2, then let me try to go as close as possible. So it is exactly like that. So here what I will do, that for a target value of consumer is beta 0.1, we find the proportion of non-conforming P2 of batches that would be accepted 100 beta % of the time. So plan 1 N is equal to 45 and C is equal to 2. So I am taking 2 plans which exactly meets the producer stipulation, satisfies the producer stipulation, and for beta is equal to 0.1, NP2 is equal to 5.322, I can find the value of P2, Now what do you see here? Plan 1 gives you value of P2.1183, plan 2 gives you value of P2.0879. So my condition here is that plan 1 accepts batches that are 11.83% non-conforming 10% of the time, because beta is 10%. On the other hand, plan 2 accept the batches that are only 8.79% non-conforming 10% of the time. Our goal is to find that plan can accept the batches that are 9% non-conforming 10% of the time. So 10% is beta, don't get confused. So now what is close to 9%? I am exactly considering the stipulation of producer and I want to go very close to consumer. So here this plan 2 is very close to 9%, and I will say that if I select plan 2, it would be very close. So if our selection criteria calls for meeting the producer stipulation exactly and closely meeting the consumer stipulation, I will go with plan 2. So plan 2 is little bit more stringent because my expectation is 9%, it is 8.9%, so it is little bit more stringent, but it will help me to satisfy the exactly producer stipulation and very close consumer stipulation. Similar way I can analyze my plan 3 and plan 4 here, and what you can see that I am getting P1.136 and P1.018. So you will select plan 4, which is very close to the expected value of my producer stipulation, and I can here meet my consumer stipulation exactly in plan 3 and 4, and I could be very close to the stipulation of my producer. So maybe a little bit sounding confusing, but the concept is very simple, I explained. Now let us look at the double sampling plan. So the idea is very simple. If you have defective and less than the lower limit, accept no issue, first go. If you have a defective greater than upper limit, reject, and if you have number of defective between limit, take the second sample, accept or reject based on two samples, not on one sample, less costly than the single sampling plan, because the average sample number in double sampling would be little bit say lesser than or drastically less than the single sampling plan. So, just see how it works double sampling plan. I have the lot of n items, I randomly select a sample of n1 items, I inspect it, I may replace defectives. Now, let us say this is the main part. So, I am coming here, C1 dash is the defective find in a sample. Suppose C1 is greater than C2 and C1 is less than or equal to C1, fine, this C1 is my one limit, this C2 is another limit. If it exceeds this, I will simply reject. If it is less than this, I will not bother, I will accept. Now, if it is in between your C1 and C2, I will go for, this is in between C1 and C2, second sample, as already I have drawn one sample of n1, so I am left with n minus n1, I will draw another sample and now I will take a decision here that C1 dash plus C2 dash. So, number of defectives found in the first sample plus number of defectives found in the second sample, if it is less than this particular value C3 or if it is greater than, I will now stop by taking a decision either reject or accept. So, this is how my double sampling plan works, and only thing that I am going for one more iteration and I am considering the number of defectives found in the first sample as well as second in order to make my final decision after taking the second sample. So, the notations which we use generally may differ from book to book, but it may be like n1 size of the first sample, C1 acceptance number of the first sample, R1 rejection for the first sample, n2 size of the second sample, C2 acceptance number of the second sample and R2 rejection number of the second sample. So, this is what exactly we do, and typically there are some key characteristic. I mentioned previously also that average sample number in case of double sampling plan may be smaller compared to the single, and the size of the first sample is always smaller than the sample size of the equivalent single sampling plan. If inspection can be curtailed during second sample, the ASN will be reduced, and double sampling plans are more costly than single sampling plan in terms of the record keeping and the administrative cost. So, let us see quickly what it means. So, let us say I have n1 is equal to 60 first sample, first acceptance number 1, rejection number 5, n2 100, C2 5, R2 6, and how it works. So, the solution is very simple. Random sample of 60 is taken, number of non-conforming found 1 or less, lot is accepted. If it is non-conforming is 5 or more, lot is rejected. If it is anywhere in between 2, 3, 4, then I will take the second sample. If the number of non-conforming item 2, 3, 4, let us say I take the second sample of 100, n2 is equal to 100. If the combined number of non-conforming found in the first and non-conforming found in the second is 5 or less, lot is accepted. If it is say more than 6, the lot is rejected. So, this is what I try to do. I can also plot the OC curve, and you can have a very simple expression PA1, that is referring to the probability of acceptance in the first say sample. So, probability that x1 is less than or equal to C1, C1 is my acceptance number, and PA2 I will have x1 is equal to C1 plus 1, because already you have taken the first sample and now you are in between. So, in between your acceptance and rejection. So, C1 plus 1 and probability of x2 less than or equal to C2 minus x1 plus probability of x1 is equal to C1 plus 2 and probability into probability of x2 less than or equal to C2 minus x1. We discussed the probability issues in detail and you can appreciate this. So total probability is PA1 plus PA2, probability of acceptance in first sample, probability of acceptance in second sample. So when we try to do it for a particular example, let us say the lot size is 3000, N1 is 40, C1 is 1, R1 is 5, N2 is 80, C2 is 5, R2 is 6, and non-conforming value is P is equal to 0.03. Find the probability of accepting such lots. So you can just plug in the values and find the probabilities. So this you can find, that is the PA 0.8889, and what does it say? That about 66.33%, that is PA1 of lot with a proportion non-conforming 3% will be accepted on the first sample. So out of so many lot, 66.3% of the lot that they will be cleared on the first sample with 3% defective, 22.59% lot a second sample will be taken, and overall 88.89% of the lot will be accepted by this sampling plan. So I think this is quite interesting, and what you can see here, that for double sampling plan, this is my PA, this is my PA, and this is my PA1. So you can see that the operating characteristic curve for total probability is on the upper side with and the lower one is your PA1. This is my single first, drawn based on the first sampling. So discriminatory power of this one is higher, and it is steeper compared to the total probability of acceptance. So you can also find ASN by using the expression N1 P1 N1 plus N2 1 minus P1 and average total inspection for the double sampling plan. So I think this thing we have discussed, so you can just apply and just try to appreciate that double sampling plan, your average sample number will be on higher side. Double sampling plan with curtailed inspection, once you know that in the first sample it is done, then you will curtail, you will not go for the further inspection, and this is less average sample number. In case of single sample, it is only n, because you are only going for one stage decision. So you can consider again a data of lot size 3000 and parameters this N1, C1, R1, N2 and C2 and R2, and you can plug in these values. So you will get average total inspection 386.93. So for a given double sampling plan, your average inspection, total inspection will be of 386.93 parts or units, and you can see the ATI. So as your incoming proportion non-conforming increases, your average total inspection is also increasing. You can design this double sampling plan in the same way for AQL, 1 minus alpha, LQL, beta, and you have the Grubbs table. So there are two tables. The first table accepts N1 is equal to N2, alpha is equal to 0.05 and beta is equal to 0.1, and you have the R is equal to P2 by P1, C1, C2, PA 0.95, PA 0.5, PA 0.1. So approximate values of N1P and PA is 0.95. So you have this table, this is in continuation for N1 is equal to N2, and similar way the table 2 Grubbs has developed, that is for N2 is equal to N1. So we can easily make use of this table for designing a sampling plan, and the procedure is very simple. First, the ratio R, which is LQL to RQL, should be calculated P2 by P1 using either of the table. The value closest to the R should be found. Then value of N1P is read from the appropriate table. Divide N1B by P, which either P1 or P2 yields the size of the first sample. the complete sampling plan involving acceptance number for the two sample can be read from the table. So, if we just see the example, then lot size is 2500, 1.2% non-conforming, 7.5% non-conforming are accepted at some beta, and the sample size are equal, and the producer's stipulation must be satisfied exactly. So, I have to design a plan which can satisfy. So, as I mentioned, find the value of R P2 by P1, P2 by P1 which is LQL by AQL 6.25. You refer table 1, R is equal to 6.749 for plan 3. So, the acceptance number C1 is equal to 0, C2 is equal to 2, and for alpha is equal to 0.05, you have PA1 minus 0.05, that is 95%, and for P1 0.012. So, with this particular values, N1P is 0.43, and you can figure out what is the sample size of the first sample in my double sampling plan. So, this is the solution that you can find ASN also, because ASN by N1 ratio is given in the GRUBS table, and this is how you can design the double sampling plan. We are not going into the detail of multiple sampling plan, it is just an extension of double sampling, but you take the initial sample, defective is lower than less than lower limit, accept, greater than upper limit, reject, in between go for the another sample and continue for n number of stages, and this is your multiple or sequential sampling plan. So, just see this example, sample 1, you have cumulative sample size 20 and acceptance number 0, rejection 2, 40, 1, 3, 60, 2, 4, and you can easily take the decision about the acceptance or rejection of the sample at an appropriate level. So, you can find the probability at P1, your stage 1, P2 at stage 2 and so on. So, just before we end, let me float couple of thinkit. Discuss the relative advantage and disadvantage of single, double and multiple sampling plan. Distinguish between average outgoing quality and acceptable quality level. Explain meaning and importance of the average outgoing quality limit, and how do you see the trade-off between producer stipulated risk and consumer stipulated risk, and devise a plan which is mutually acceptable to both. So, these are the references. Mainly I have used Mitra for this particular lecture, and we have to devise a effective discriminatory sampling plan which helps producers and consumers both to have the consensus on a particular value of N, C and so on. So, thank you very much for your interest in learning this particular lecture on design of acceptance sampling plan for attributes, and we will continue our discussion on this with couple of more plans. Till that time, keep revising, introspecting. Be with me, enjoy.